Good evening, ladies and gentlemen, and welcome to Astronomy on Tap Atlanta. Thank you for joining us on such a frigid night. We appreciate your trek and your journeys, and we hope that we make it worth your time. Tonight, we have a very special presentation from a recent collaboration of ours between Georgia State University and the Fernbank Science Center, its planetarium, and its observatory here in Decatur. We are very, very proud to welcome the Fernbank Science Center Observatory and Outreach Specialist, Steve Bieger. Let's hear a round of applause for Steve. AI is prevalent in our lives and being thrust upon us in many ways that we like and don't like. Steve's job today is to tell you what useful things we are using AI for and how it's going to reshape the future of astronomy and hopefully give us some very, very useful and insightful results. So please, without further ado, let's hear one more round of applause for Steve Bieger.
Thank you, Dr. Robinson. Thanks for the opportunity to come and meet with you all tonight and to give this talk. I've been putting this together for a number of months. I'll go into a little bit of a, from the top of my head kind of idea of where I've come from on this and the reason I've decided to do this particular topic. So a little bit more information about what I do at Fernbank Science Center. And I've been there starting as a volunteer in 2005, working in the observatory. And since about 2013, I've actually been there as a contractor. Along with my colleague, Josh Freeman, we handle the Thursday and Friday night public viewings there. And it's free of charge. You're welcome to come up and join us if the weather's good. So tonight, I know the weather is nice and clear, but it's going to be really cold up there, so I'm glad to be in here. This is the kind of indoor astronomy I really like in this location here. So the topic, though, is something, as I said, I've been diving into, but you find out that reviewing what astrophysics is, you know, as I'll show, we go back to about the 1850s and look at the history of it. And then the further along you get into the 90s and you start looking at AI, and all of a sudden you get a flood of different topics and subtopics. I could be standing here for days and not cover all of it. So this is a cursory level of some things that I've discovered over the last several months, and I'm happy to share that with you. So the topics that I've chosen here, I'll break this down piece by piece. But as the title of the program infers, there's a historical aspect to what this talk is covering. So I'm gonna work through that step by step. When I do a presentation like this, I like to think of it as layers of the onion. So I'm peeling off bit by bit, and I'll sometimes dive down. So if I lose you a little bit, give it time. It'll come around. I like to dig a little bit deeper, but I'm only going to go a short, shallow bit on this. Like I said, it's a very cursory look at this. And let me see if I can get this, hit the right key. There we go. I want to start by emphasizing the historical context of astrophysics as it takes us all the way through the second half of the 19th century up through the present day. And then I will start to weave that in with how what we consider modern computing has come into play a part in a big way. But I want to pay homage to a number of scientists, as I will outline here in the coming slides, who've created the knowledge base of astrophysics that now we can use AI to mine that data. The data came first. So the hard work of all these scientists over many, many decades and the heavy lifting that they did, sometimes literally heavy lifting, before the age of computing, before the age of the internet. And their theoretical analysis that they did on pen and paper is really where we can go back and think of that work as being the basis for this sort of next generation of exploration using AI. As I'll show, the historical context takes us through a certain time range. Then we get into what I call the modern context, which is sort of the latter part of the 20th century, and I'll break that out a little bit more. but I'm going to be talking a little bit more about data sets and where they come from, and then start to also look at how the way that data processing started to improve and become more mature as we get into the mid-'80s and beyond. At the very end, I'll talk a little bit about what's next. There's some really, really exciting things in the pipeline, and that we'll all be, I'm sure, watching very closely over the coming year or two. First of all, though, just to make a distinction, and I'm going to try to do this from the top of my head because the notes here are just there if I really need them. I want to compare two different terms, astronomy versus astrophysics. So astronomy classically is thought of, it is a science, of course, and it's the way that we look at the sky, we identify objects that are there, and to some extent we study how they move, where they're located in the sky. We see that whole pattern change season after season, year after year. That's what we do at the observatory when we're steering the telescope up to Jupiter or the moon or whatever. We're looking at these patterns and the constellations passing through. So it's a study of what's there, okay, and where is it located in the sky. Astrophysics is a spin-off, if you will. It's a branch of astronomy that really got its footing around the 1860s. And as I'll show, there were several things that really led to that. But now we take physics and we introduce that into the observational work that we're doing, and then mix all that up and make new theory as a result of that. So astrophysics is really a relatively young discipline. Astronomy goes way, way back, perhaps 400 or more years, okay? The knowledge base of astrophysics really starts to build when we get to the implementation of early photography. So around the 1850s, photography was at a very, very early age, and the emulsions being used, the techniques being used were very, very crude. But over a period of about a decade, those emulsions improved. There was a number of people working on different photographic techniques and materials and everything. You know, they were coming to know how silver compounds were working and making these really great emulsions. So initially, the early astrophotography was done only with very bright objects like the moon or the sun. The emulsions were very, very poor. After about 10 or 15 years or so, things started to change quite a lot. And I'll show a little bit about how that gets introduced in some future slides here. So the historical knowledge base goes back even to the early part of the 19th century, as there were the beginnings of understanding of how the universe appears to us, the study of light, and early attempts to understand spectra and so forth. Then we get into what I call the modern age, which is really around the time of World War II, 1950s, and that sort of thing. Things started to change quite a lot. But the knowledge that was being accumulated and the analysis that was being done really started to bring in some new, very exotic topics, things like black holes, things like supernova, even the early stages of looking for dark matter, sorry. We get to a point in the around the 1870s, and we start to see some very, very important figures in the sciences doing some very meaningful technical work. The first one was Henry Draper, and in 1872, he was taking the first spectra of the sun. So he was a self-motivated, very, very early stage astrophotographer, one of the first. And this is a picture of one of his cameras that's hanging off the end of this. It's about a 12-inch refractor. So the work that he was doing in the early photography, of course, leading to his spectrographic work, came to a sudden end. He died an untimely death, and but he had already been doing some great work, and he was doing it in association with the Harvard College Observatory. So he didn't have any children to leave behind, but his wife stood up and really came to play a big part in his legacy. Mary Draper was a key person in the sort of modernization of the Harvard College Observatory, and as we'll see, worked very, very closely with Edward Pickering to develop a number of different programs to get some funding. She helped get funding for a telescope there, and also working with Pickering, developed the Henry Draper catalog. So there was a lot of things going on in the late 19th century, the early 20th century at Harvard. It was starting to really become a key institution in terms of serious studies. Pickering himself developed a method, kind of picking up where Draper had left off, of putting a prism in front of the light path in a telescope so that they could take multiple spectra with one image. And perhaps you've read about the work that they've done and the thousands of plates that they created, but each of those plates would have numerous stars on, each one with a tiny spectra next to them. The last count that I heard of the number of plates, these are about a 16-inch square glass plate, very fragile, each one sitting in its own little envelope, nicely packed, one right after the other, in a gigantic building that was made fireproofed and everything. It's still there. Most of the plates are still in existence. They've been digitized a lot in the last few years. There's over 250,000 of these plates cataloged. And it is estimated that the weight of this photographic evidence is on the order of 120 tons. And they have this gigantic building where they've kept all of this. But that is a knowledge base going back to the early part of the 19th century. Very, very important data. He was the director of Harvard College Observatory for a number of years. And one of the main things that he did was to bring in a group of women to work for him and form this team so that they could examine all of these numerous glass plates. They were taking these spectra all the time at the observatory. And the so-called name of this group were the computers of Harvard. Very important group of people featuring names like Annie Jump Cannon, who were working with Pickering at a very, very early stage to develop a classification system for stars. And this is where we get the OBG layout. That was the eventual evolution of their work. And you can see these women packed into this tiny room. And in the foreground here, you can see one of them is looking at a glass plate. They were going through these plates, you know, very, very, very carefully, making notations on them. And that work eventually allowed us to get a very fine series of discoveries. And one of the things I'll do, I like to promote this particular book. If you haven't heard of it, you might be able to see it here. It's called Glass Universe by Dava Sobel. That is the story of these women that worked at the Harvard Observatory. It's an extremely well-written book. It talks about what Pickering did, what Draper did, and his wife, and the women that were working there. And it's a really interesting look at the evolution of astrophysics in the United States, for the most part, during that time frame, in the early part of the 20th century. There's even some timelines in the back of the book. It's a great read. Henrietta Swan Leavitt stood out as one of the key members of this team, as Dr. Robinson has talked about in one of his talks back at Fernbank a few months ago on active galactic nuclei. Her work studying Cepheid variables was instrumental in the work later on done to get us further out with the cosmic distance ladder. And I agree with Dr. Robinson. The work that she did in discovering this period luminosity relationship, as it's called, she studied these plates and came up with a relationship where the pattern, looking at the up and down magnitude changes of the Cepheid variables, are related to the distance of these stars. So now, with that particular bit of information, you could go the next step from measuring the distance of a star from parallax, which gives you a limit of maybe a few hundred light years. You can go beyond that now. You can start looking at variables in another galaxy, and you can then use that timing relationship to figure out how far away that particular galaxy is. And that's what Edwin Hubble did. He realized early on that this period luminosity relationship was very, very important. And when he was studying plates that he had taken of the Andromeda galaxy, M31, there's a famous picture of this plate that he had taken, and it's kind of this reverse image, and he had written VAR with a great big exclamation point. He had actually spotted a Cepheid variable in the galaxy and could then measure its distance. That was the beginning of the work that he was doing to show that not only was the universe way bigger than the Milky Way, but then later on he was able to show that it was expanding as well. All big stuff, very, very incredible stuff going back, to the 30s. About the same time that all this activity was going on in Harvard, there was a British scientist by the name of Arthur Eddington who was a real polymath. He was a physicist, he was a mathematician. He also was a promoter of the sciences. He had even spent time later in his career giving lectures and writing about the work that Einstein had done on relativity. So think of him as kind of an early day Carl Sagan. All right, so he was popularizing that kind of very difficult information. But he was studying the processes involved in the workings of a star inside of its nucleus. And he had put forth this idea about how nuclear fusion was driving the energy release inside of a star. And at one point, he gave a lecture, and there was a woman in the audience who was paying attention to what he was having to say. And she was getting an interest in astronomy and decided to make it her life's work when she heard this lecture. Her name was Cecilia Payne. At the time, she was not married. Gapochkin was her name later on. That was her husband was from Russia. But she took to heart what Eddington was saying and began to piece together a career path for herself. She decided to move to the United States and get to Harvard because she wasn't going to make it very far in Britain. But she was hired there after a couple years and by the Harvard group, and started to piece together a very, very important paper that was published in 1925. That was her PhD dissertation. I'm going to have a link on my website that I'll talk about later that has links to this. And the paper was written with real groundbreaking kind of analyses of what was being discovered then and what was known then about solar spectra. And we're looking, of course, at information from a spectra that's coming from the outer surface of the sun, the photosphere. So she started piecing together the known facts behind all of these various observations and started to show that the pressure and the temperature of the gases in this outer region of the photosphere were having an effect on these dark lines that were showing up in the spectra. Either they were very narrow or they were widening. She put all that together in this paper with the reference at the very beginning showing that here's the laboratory look at these different gases. And here's what their lines look like in the pure form. And then you can extrapolate from that and see what's going on the surface of the sun. So this was describing how the sun operates in the upper 100 or so kilometers of the photosphere, and that's what we see through the spectrograph. So her work was dealing with that. Eddington was already talking about what was going on in the center of the sun as well. This continued to develop, over decades. Later on, as we get into the 50s and 60s, another woman who really, really paid a lot of attention to those fine things that later resulted in something fantastic was Vera Rubin. And her work was, I don't know how, I'm still reading up on this, but I don't know exactly how it came about, but she decided to look at the motion of galaxies and see how those galaxies were turning. And she came to a discovery that showed that this galaxy movement isn't as it's expected. The outer regions of the galaxy, initially you would think, well, they're going to be moving more slowly. That's not what's happening. So her work in charting out the work of these galaxy rotations indicated that there was other mass there that can't be seen. We now know it as dark matter. So she was able to confirm some of the theoretical work that was being done at the time by Fritz Zwicky and others, and was able to then put forth this idea. And it's one of those things where she did the kind of work that deserved a Nobel Prize, but because she was female, it didn't quite work out that way. But she's still recognized now as being a pioneer in this particular era. And as we'll see, there's a great new telescope coming online in Chile right now, named after her. Another name we don't hear too much of, but as soon as I mention the last name, Chandrasekhar, you'll probably think, oh yes, Chandrasekhar Limit, the Chandra telescope, that's who it's named after. He was a physicist and very actively looking at a variety of different objects and coming up with theories and mathematical representations of the workings of supernova and so forth. And so he contributed a lot as well to what we now see on some of these exotic objects. Jocelyn Bell Burnell, another person who didn't really get what she was due, but she discovered pulsars. And she showed that they were really important. They were really far away using radio telescopes. She also did work that was certainly a valid reason to give her the Nobel Prize. But her discoveries were made when she was still a student. She wasn't a PhD yet. So technically, she didn't qualify. Nevertheless, these days, she's still held as a very, very important figure in the development of radio astronomy. And she and Vera Rubin as well were also very active in the promotion of women in science and to get the kind of due that they deserved. Moving forth into a little bit more modern times, Roger Penrose has done a lot of extensive work on his mathematical analysis of black holes and so forth, close associate of Stephen Hawking. He shared the Nobel Prize recently with Andrea Ghez and I'm trying to remember the gentleman's name in Germany. I've got it written down. But they did work on looking at the supermassive black hole inside our own galaxy. So he did a lot of the mathematical work on that. And when you finally get to the later part of the 20th century, Stephen Hawking is also a person that really stands out. He was a theorist, he was a cosmologist, not so much an astrophysicist. But the kind of work that he did with Penrose and later with Kip Thorne, as we'll see, that also contributed to this additional branching out of astrophysics as we get into this observational cosmology, which was really started by Hubble. And all of this is starting to expand more and more. And all of that knowledge base continues to develop and be all tied together. There's a great big, a web of information there all tied together that we're going to tap into with these new machines. Kip Thorne, he's still around and interesting fellow. I've seen a couple of interviews with him. And he's still doing work out in, I think he lives in San Francisco. And interestingly enough, he also worked with Hawking and has done a lot of work mathematically to describe what a black hole does. And if you have seen the movie Interstellar, okay? Yes, we have one person in the audience who have seen it. If you haven't seen it, I recommend getting a hold of the disc and get the special copy that has the second disc on it that shows about the making of the movie. There's an interview on that disc with Kip Thorne. He developed the mathematics, just writing it down, that described how a black hole would look if we were to image it at a relatively short distance, okay? Describing all the relativistic effects as this massive disk is spinning around the black hole, and we see light being bent from behind its massive influence, its gravitational influence. He came up with the formula that he passed on to the filmmakers, and the graphic designers used that to then create an actual image on the movie screen of a black hole. When he saw that, he said, man, that's what it's going to look like. So it's actually a very, very accurate representation of what a black hole might look like. And then as we'll see later on, you get an image from the EHT telescope, the Event Horizon telescope, and guess what it looks like? It looks a lot like Kip Thorne's mathematics. Pretty amazing stuff. So there we're taking real data and putting that into the video screen And now, as we'll see, AI is being used to process that even more. So data processing in astrophysics now starts much further along in this whole stream of events going back into the 19th century. But the mathematics were constantly being developed, as we'll see, even in the 40s and 50s. In fact, even back into the late 30s. So there's a historical time frame on this as well, which kind of starts a little bit later than the time frame for the actual observational work. So again, I'm talking about historical going up into the 50s or so, then a modern era, which takes us up into the later time frame, the 80s and 90s, and then present day, certainly from the second half of the 90s all the way up to the current time. From a historical standpoint, going back into the 30s and 40s, and I'll show some photos here in a slide in a moment, the kinds of machines that were being developed before World War II and during that time were very, very kludgy, gigantic things with relays and switches and wiring harnesses. These things were weighing tons. They were mechanical devices in a lot of cases. They were actually analog computers in many cases, but calculators. And the early stages of these machines were being used for things like calculating missile trajectories and that kind of stuff. So there were military applications that were being used for these. And part of that was that the only people that could fund this kind of project were the military. Okay, so you had to have a lot of bucks and a big facility to put something like this together. The technology, though, was very limited. Like I said, a lot of vacuum tubes. I'll show you a picture of one computer in a moment. It was only working half the time because the crew spent the other half of the time replacing vacuum tubes every day because the thing just was going down all the time. However, at the same time, early programming languages were starting to get developed. Key ones are COBOL and Fortran. Now, Fortran is important to us because, as we'll see, as we get into the 90s especially, Fortran developed into a tool used with very high-performing modern computers for number crunching. So this was kind of the early stage of being able to do data processing on a machine or a group of machines in a cluster, as it turns out. But in 1956, things really started to change. The first workshop on AI was held in the summer at Dartmouth. And I'll expand on this in a little bit later. And I highly recommend, if you're interested in how AI came together and the sort of talent that was used, that was tapped into, I should say, it's worth reading about the Dartmouth workshop. And they've actually had a follow-up to that in the last decade or so to see where things are going. But this was a way for the mathematicians and the early computer scientists of the time to get together and try to codify and document what artificial intelligence was. That's where the term was actually coined in 1956. You can't go very far looking at the world of computing and where we've come from and what we have now without talking about Alan Turing. Just on the surface, there are so many things that he came up with, and the theoretical work that he transformed into machines. He's most famous perhaps for his work at Bletchley Park during World War II. He was the designer behind the machine that cracked the Enigma code. All right, that was the coding system that Germany was using to send their secret messages. There's a great movie about it called The Imitation Game, which covers that really, really well. It's a finely made film, and it covers a lot of his life very, very well. He was a very controversial man. I won't go into that, but he was absolutely brilliant. But his work on early computing and the concept of intelligence in a machine turned into what is called the Turing test. And I'm trying to remember the exact year, but I think it was 1957, I think, where he finally released this after doing a paper. The idea being that if we can create a machine that generates the pattern of thought and gives you an answer that is indistinguishable from a human response, you've got intelligence in that machine. That is the sort of base level definition of intelligence in a machine. This is a recreation, it's actually a rebuild of one of the machines that he built for Bletchley. You can see the door open on the right there. This thing, I don't know, it doesn't say how heavy it is, but it's an electromechanical system with all these wheels turning and everything and all these relays. This huge wiring harness and everything. This was the mechanical machine that he built to break the Enigma code. And they actually, I was surprised to read this recently, they made actually quite a few of them. They had hundreds of these that they had built over a period of 2 years, I think, to continue processing all of these messages they were getting from the Enigma. And it later on developed even more as well. But he was taking, Turing was taking his ideas about computing and actually creating machines for this. Later on, when we get into the 50s, we have a machine like this one. This is the ENIAC that was housed in the University of Pennsylvania. And you can see it's just rows and rows and rows of vacuum tubes and relays. And this was just one section of that particular computer. But this is one of the first machines that actually was able to use a stored computer program. So when you're using an app on your phone, that's a stored computer program. So this thing was able to use that kind of concept to work. And in fact, it was actually Turing that created a lot of the mechanical and theoretical work behind the idea of using an application. This was the Maniac computer, which was used in Los Alamos. And you can get an idea of the size of it, banks of relays and wires and stuff along the left side. And where the woman is standing in the foreground, she's holding literally a programming chart. So she's walking by these panels and moving all these pluggable connectors there that set up the program. So not exactly a convenient thing to use and kind of hard to carry around in your pocket. So in the modern era, around the time of the Dartmouth summer workshop, AI as a concept is actually born, all right? It's actually given that name. And there's a lot of activity going on for a number of years where they're making some really good progress. They're getting some money from government entities like DARPA, and certain institutions as well are starting to build their own artificial intelligence programs at their universities in the US and in Britain. And things were going along swimmingly until maybe the 70s or so. Then they started running into roadblocks. They started running into some headaches where the expectations just didn't really come through. And hit the right button. They did have some successes though, and they were able to show a lot of concepts like neural networks and that type of thing were beginning to take shape. And but these roadblocks started to slow them down, and as a process, the money started to dry up. All right, and so the people working in AI started to kind of slink away into other places and build other kinds of work, and they weren't even using the term artificial intelligence anymore. It was becoming kind of a four-letter word. And so they went off and studied neural networks, or they studied robotics. So they continued to work on this, but at the surface, it really didn't look like it was going to do too well. But in the 80s, things started to come back a little bit. In that modern era, we now are starting to see computing power and software power that's coming commensurate to what is needed in order to do work in astrophysics with serious astrophysical computations, all right? So all of that had continued to be transpiring anyway, but the computing power just wasn't there. The CPUs weren't fast enough, the memory wasn't big enough, and so we had to wait a while into the 80s before the hardware started to catch up with the concepts. So in that whole processing, though, we start to see these higher level languages like Fortran, and we started to see some studies being done on numerical models of stellar structure. How does a star work? What goes on with a supernova? That type of thing. They were beginning to get the essence of what computational techniques were needed for that. Supernova dynamics were also a big part of that as well. How do you model what goes on in a massive star just before it goes pop? And they were starting to work through that. And again, the hardware initially wasn't very powerful, but they were developing the techniques and the languages and so forth. Look back in time to the mid-60s. Some of you may recognize what this is. It's called core memory. This was part of the guidance system for the Apollo capsules. There's probably no more than 1K worth of data being stored in this thing. And you can see the connector at the bottom here. That connector is probably about 2.5, 3 inches wide. So you can see all these little wires weaving back and forth through this matrix. And that was part of essentially the calculator that they had on board the Apollo missions. 10 years later, the Voyager missions flew with their own kind of computer, and you can see those same connectors at the top there to give you a little bit of a scale. So this board is probably about 12 or 14 inches across. This was part of the guidance system for the Voyager mission, and you can see there's a lot of surface mount objects there. Probably some of the early integrated circuits were appearing at that point. Very high tech though for the time. Go forward another 10 years, 1986, IBM comes out with this little prize little item here. I remember when they came out, I was just starting to work in IT, and I was working for a company making printers, and these machines came out, far too expensive for me to consider. The Apple II computer was still a big deal when they came out, but behind the scenes, the use of microprocessors now set the stage for the next quantum leap in computing power, and that's when astrophysics was really going to start taking advantage of that. So from the mid-80s to the mid-90s, you get into this kind of hardware. This is the another IBM system called the SP. Each of these cabinets has 16 individual computers on the inside of it, all tied together in a cluster, if you wish. I worked at IBM for a while, and we had several of these that we were using. We were just using machines individually, but they were running Unix, IBM's own flavor of Unix, and we ran our whole email system around the world based on these things. We had 2,500 of these things around the world, so they were kind of fun to work on. But the capacity of this kind of hardware was really important when you clustered them together. You would have a supervisory program that would talk to all of these nodes, and you could use Fortran on multiple machines, and every one of these CPUs would get a piece of the computation and run it all in parallel. So parallel computing was starting to become a big deal. So to quote someone from the Voyager mission, in 1915, Richard Terrell said, "In everyone's pocket right now is a computer far more powerful than the one we flew in Voyager in the mid-70s. He says, I don't mean your cell phone. I'm talking about the key fob that unlocks your car. So this was, he was quoted in 2015. He's still around. He was part of the Voyager imaging team at the time. But that kind of illustrates where we were going decade by decade by decade, the increased capacity of data processing now to present day. So let me see if I can go through this here. I'm going to look a little bit at some of the processing techniques and also look at some of the topics that we're dealing with in modern day. So neural networks have been around for a while, but now they're taking a higher level of importance in AI, and astrophysics is taking a big a step towards using that. And the general term computational astrophysics has really advanced from the point of the 90s, where now we don't just have clusters of computers, we now have far more sophisticated software to do a lot of that work for us. So we've moved from the age of Fortran, now we're in the age of the algorithm. Big data was starting to really become a thing in the 90s. Big chunks of data. Most importantly now, when we see data, we can use machine learning to dive into that deep data, because the data now is getting cataloged and tagged. Really important. NASA is even going back and looking at some of their old data from earlier missions and doing the same kind of thing with that. When you have that data in a big data set, you know, terabytes of information, and you can tag it, when you touch it with AI, AI already has a head start in figuring out what to do with it. And automated discovery is another big thing coming out in processing techniques. I'll talk about that in the next slide a little bit. This is where the tools running in the software themselves start to pick out things that you don't normally see. So part of the way you do that is with modeling and simulation. And a classic thing that's being done right now is to actually test predictions. You build a theory, you come up with a model, you run that through your computation, and then you see what the expected results are. So you could build a simple model, let's say, of a supernova, and gradually improve that and build up on its complexity. And the other thing that's really important too is we're not just looking at solid images that are a snapshot in time, but we're looking at multiple views of a series of events, transients and other anomalies that really lend themselves to studying a variety of different phenomena. And as we'll see in the coming years, I think we'll see more of this. We're using AI on board in space telescopes to help to optimize the viewing before the data even gets sent to the Earth. So those transients, like planets, can easily be hunted now in a big way compared to what we've had before. Stellar classification, what we know from the days of the Harvard computers, we know even more about it now, but they started the whole game. Galactic clustering is another area where we're starting to study how very, very massive groups of clusters form together. This is kind of the beginnings of looking for dark energy, as well as studying what is already visible in terms of dark matter. Supernova dynamics, of course, are continuing to get more and more important. Black holes, the Event Horizon Telescope imaging, I was just reading about it the other day. If you go to their website, they're showing how they're already using AI to reduce noise and increase the resolution and clarity of the images that they've already taken of M87, which was their first target. Gravitational wave detection, I'll show you a picture of LIGO here in a moment. They're continuing also to improve their data collection, again, reducing noise, improving the resolution of the mapping itself. Dark matter is getting more and more attention now as we're getting data that really starts to show it. And a new thing that's, I kind of caught this a few months ago, a new field called crowded field photometry. About 2.5 years ago, there was an image taken of a globular cluster known as M92 by the James Webb Telescope, and it was taken specifically as a data source. And there's been a couple or 3 different institutions that have taken that data, and they're using some astronomical computation tools, and they're adding AI modules to it. If you can imagine a globular cluster made up of hundreds of thousands of stars all in one image, how in the world do you pick that apart and you get the individual data off each and every star because they're all interfering with each other? Well, they're working on ways to do that. What's really happening, though, is the James Webb Telescope is bringing new discoveries all the time. They're starting to use also some of this onboard technology to help the telescope set up for imaging, using it, for example, to select filters when they're doing planet hunting so that they can catch the planet at just the right time and maybe get a spectra of its atmosphere as it passes in front of its parent star. Event Horizon Telescope doing more and more things. They're building more and more tools to work on the images that they've already taken. LIGO is continuing to bring forth more data. So these are operations that are already in place, but they're benefiting already with AI. That's the James Webb, of course. That's a lovely model of it. It's up there doing incredible work. There's a Netflix special, I think, that talks about the launch of this, and if you can find it. There was over 250 single points of failure on that launch mission that got the telescope to its final place where they could get first light. Every single one of those single points of failure did not fail. That was amazing. The story behind that and interviewing the people that were on that mission are amazing. So Event Horizon Telescope, this is how you build a very long base interferometer. You put a telescope in a bunch of different places and they're all pointed at the same place. That's how we're getting these wonderful views of these black holes. LIGO is, this is one of the 2 sites here in the United States. That's the one in Louisiana. And what's next? What's really exciting is what's going on at Vera Rubin. I check about every 10 days to see if they've got a new press release. No, not yet. They're getting there. When they do release something, though, it's usually something really important. So Vera Rubin is pretty much online. They're probably going to begin their actual runs if they haven't already. I highly recommend going to their website and just looking at the gallery. There's just incredible photos of this instrument using the world's largest camera. It's really amazing. And keep your fingers crossed, the Nancy Grace Roman Space Telescope is in its final stages of preparation and testing. It's built, it's ready to fly. Hopefully, May next year, it will be going up in space, and it will be sort of the takeover instrument to Hubble. There's Vera Rubin, lovely shot there out in the hills of Chile. And you can look at the bottom there, you can see some of these big tractors, so you can get an idea of the size of this thing. It's a very, very big instrument. But go to the gallery and have a look at this instrument. That's a depiction of what Nancy Grace is going to look like. They're calling it the Roman now, so they've just kind of abbreviated it. But read about Nancy Grace Roman. She was instrumental in getting Hubble to fly. So that's why they're honoring her with this particular instrument. So to wrap up here, I wanted to just remind us all that we all stand on the shoulder of giants as we are getting into the field of astronomy or astrophysics or whatever. And this was attributed to a letter, a part of a letter that Isaac Newton wrote to Hooke, because they had this wonderful, nasty relationship between themselves. But that's worth reading about as well. But Isaac Newton said, "If I have seen further than anyone else, it's because I am standing on the shoulder of giants." So it's worth reminding ourselves with some quotes here that I'll bring up, that the work that we do to create the data that's now forming these massive data sets, that's the beginnings of all of this work. AI isn't really the key element in this. AI is just a tool to crunch through this data. It's human creativity and it's human imagination that gets the ball rolling. So with a couple of people here, in the case of popularization of science, I like to look for some quotes. Here's a couple from Neil deGrasse Tyson. And as he says, we're all connected to each other biologically, to the earth chemically, to the rest of the universe atomically. That's something that kind of gives us a little bit of a perspective of where we are. And here, the remarkable feature of physical laws is that they apply everywhere, whether or not we choose to believe in them. After the laws of physics, everything else is opinion. But finally, Carl Sagan, one of the most brilliant popularizers of modern science and a brilliant scientist in his own right. He has lots of great quotes to his credit. There was a couple here I picked out, those specifically to us. The cosmos is within us. We are made of star stuff. That's a very famous one of his. But I like the other part. We, all of us, we are the way for the universe to know itself. Somewhere, something incredible is waiting to be known. So with that, I wish you good luck in your endeavors to develop your scientific skills and to uncover amazing things about the universe. Thank you very much for your time.
Thank you very much, Steve. I think it's kind of a cheat to end with Carl Sagan because all of his quotes are great, but
Yeah, that was a hard choice.
Yeah, I know.
Yeah.
Anybody have any questions for Steve?
There's one over here. Yeah. Going to go out for a ride, huh?
Yeah.
All right. Here's our portable. Yes.
Great talk.
Thank you.
In terms of how AI is starting to help the field of astronomy do harder, more difficult things, look at further objects, look at things we've never seen before, is there anything that you're excited about in the field of astronomy and astrophysics that you think AI will sort of break open for us?
Yeah, that's good. There's some common ground there amongst all of the work that's being done with astrophysical computation. Pattern recognition is a big thing. Reducing noise is starting to become now kind of the second wave of improved AI operation. Transient measurements where we have multiple images that look almost the same, but you have to apply some really deep serious kind of attack on that data to try to pick out those fine details. So that's the machine working and doing all that number crunching. The benefit of that is that it frees up the scientists to go figure out, okay, what are we going to do next? So a lot of that tedium is reduced, and you can then focus on the creative side of things to really make things go forward. There was a paper, and I'll have a link to it eventually, when I was doing this work on space exploration, where a researcher, I think he was at Harvard, was saying that the real benefit of AI is going to really stand out in the world of science. We're not seeing that in the commercial world because we're not in this to make money. We're in this to learn about the universe. The advantage is going to be freeing up the mental and creative capacity of human beings to do what they do best. And then AI is going to become a partner in that to do the number crunching. With new telescopes coming online like Vera Rubin, it's going to be producing tens of terabytes of data every night. So over a 10-year period of its mission, it's estimated to be producing several petabytes of information. That's going to be impossible for us to deal with when you're trying to make a cosmic movie. You know, let's let the machine do that work, and it'll pick out all of that. Vera Rubin is very exciting. Yeah, that's a big one. Yeah.
Any other questions floating out there?
Hey, Steve, thanks for the talk. I do have a question, but a quick comment. Alan Turing is a big hero of mine. I do want to comment that, like, in my opinion, he single-handedly probably did more to win the war than any other person.
Mm.
And there's some mention about controversy, and sometimes people don't know the story. I don't think he was controversial per se, but you know, he was a gay man
Yeah.
at a time where it was illegal in Great Britain. He was persecuted by the government and committed suicide.
Yeah.
And we lost a really important hero. And I just wanted to call that out. Sometimes when we say someone's controversial, it's because they maybe did something sketchy or something.
Yeah, true. Yeah.
Sorry, but the question is, can you talk a little bit about the different types of telescopes and how they're being used? I know that the Vera Rubin, you know, it's obviously up in a big mountain in Chile doing some things, and then there was the telescope where you had across the whole globe doing different things, and of course the space-bound telescopes. What are they looking at differently to where they're all adding value in their own way?
Ooh, that's a good one. To use a pun, the scope of those images is very different. What I found is that there are some similarities here in the research that's being done, where you have essentially kind of static imagery that's being looked at, where, say, you've got a view of a galaxy and you're looking at it over time. So you have a longer time frame where you're looking for changes. In a shorter time frame, though, you may be looking at a parent star and trying to catch the planet going around it. So there you have a shorter time frame. So some of the tools that are being applied come from other areas of science, not just from astronomy. So AI in astrophysics is starting to benefit from some of these other number crunching techniques that have been used in the fields of medicine, population studies, and that type of thing. So there's a mishmash. It's really hard to kind of pick everything out. But the age of the telescope itself has a certain bearing to it. Hubble is very old, of course, and it doesn't really have, that I know of, any AI capability on board. So you have to do all that earthbound. James Webb is a little bit different, and some of the newer telescopes are different yet again. They're incorporating AI into the operating systems that run on those telescopes. So that's cool when you can do that when the thing's already flying, you know, and you can change the program and everything. With Vera Rubin, I haven't seen yet how exactly they're going to be using AI real time, but I'm sure there's going to be something going on there, because there's actually a secondary telescope that's running it was not in that photo. There's a smaller dome nearby, and they're using that to look at the real-time conditions in the atmosphere. My guess is they're going to use some of that information to drive optics in the main telescope as well to help improve that imagery, all that kind of feedback stuff. So that's real-time kind of actuation. So I can't really answer that question without kind of vaguely saying, yeah, it depends. There's a lot of stuff. But newer telescopes coming online, like the Roman, is really, really going to be geared for AI. Euclid is doing a lot of that already. So the age of the telescope and its generation really has a bearing on that.
Benedict Cumberbatch should have won the Oscar in 2014 and not Eddie Redmayne. And
Yeah.
I will die on that hill.
Yeah. That was a brilliant bit of acting.
Absolutely. Steve will be hanging around for additional questions, but right now it is clear, it is photometric, and Jupiter is high and bright in the sky, and we are training a telescope right now to look at it. So if you want to join us in the parking lot to see Jupiter and its moons, please do so. I will also say, Three Taverns is the best beer in Atlanta. I'm not biased at all. But please, in the meantime, while you're asking Steve a question and while you're waiting for us to get Jupiter in the scope, please buy a beer, please buy a six-pack, take it home with you, and we will see you a couple of times in February at the Imaginarium and back here in Decatur. Let's give Steve one more round of applause. Thank you, everybody. Have some beer, see Jupiter, and have a good night. Thank you.
Just a quick, I'm going to leave this screen up here. This is my blog site. If you want to write down that address later on, you'll see over on the right-hand side, there's some info pages there about AI. That's where I'm publishing some of these links. There'll be more of those coming on later on. And at the very bottom here, where it has my name on it, you can click on that and get my email address if you wish to contact me directly. But I've got a whole bunch of links. I've got hundreds of them. I'm probably going to have to put into a Word document. So I'm not going to put them all online, but I'll probably be able to get that that document in such a way where I can actually send that out to anybody that wants it. There's a bunch of great stuff out there. And yes, AI is your friend. Use Google. Thank you very much, everyone. I enjoyed it.